Hello, everyone. And in this presentation, I'm going to introduce our work regarding examining the vertical heterogeneity of aerosols over the Southern Great Plains, or the SGP. So first, I would like to acknowledge our collaborators who have been very helpful in analyzing these results. So as we know, both the aerosol direct and indirect effects are influenced by the vertical distribution of aerosols. This is especially the case when we talk about the aerosol-cloud interactions, where the measurement conducted on the ground might not represent what's really happening at the cloud level. And then the vertical distribution of the aerosols is further influenced by processes such as aerosol dynamics, long-range transport, and entrainment. And therefore, the ground observations may limit our ability to understand the vertical distributions of aerosols and further simulate their climate impacts. So in this study, we were trying to examine the vertical heterogeneity of aerosols over the SGP by using the high-scale data. So there have been several studies examining the vertical distribution of aerosols over the SGP. For example, the studies from Jim Smith's group and Jeff Pierce's group have shown that new particle formation can happen in the upper boundary layer. And these newly formed particles can further get mixed into the entire boundary layer, and then where the ground may not be able to observe these newly formed particles. And an earlier study by Jian Wang's group also showed that over the SGP, there are aged aerosol layers, which will have significantly different optical properties. However, for these measurements, they were either conducted during a short period of time or there were limited data. And during the high-scale campaign, there were a total of 38 research flights conducted during the spring and summer, which can provide us with some information regarding the seasonal variabilities and also the vertical heterogeneity of the aerosols. So in terms of method, we examined the vertical profiles of the meteorological and aerosol physicochemical properties up to 2,500 meters above the ground level. And we were using the flights or using the data from the 38 research flights. We focused on the aerosol physicochemical properties, which include the aerosol size distributions, number concentrations, different size modes or different size bins, and also the chemical composition. And due to the time limit, I'll just focus on the first two. And we're trying to identify the processes that influence these vertical distribution of the aerosols. And I'll show that by case studies later on. So here the figure shows the, let's say the scale of the, or the magnitude regarding horizontal scale of the high scale campaign. And then these lines represents a flight track for all the research flights. Different color represents different flights. And on the right-hand side, it shows a representative research flight where you can see there are these vertical profilings. And then in this study, we're just analyzing the data that were collected during these vertical profiles. So first, we spend our time analyzing the aerosol size distributions. So to show these aerosol size distributions, basically the x-axis is the aerosol size, y-axis is the altitude above ground, or the AGL level, right? So the 3 to 10 nanometer particle size distribution is actually coming from the difference between two CPCs that has different cutoff sizes, one with 3 nanometer, the other with 10 nanometer. And then for the aerosol size distribution of above 10 nanometer, they were measured by the Fast Integrated Mobility Spectrometer, or the FIMS. So we also, basically here, the size distributions are averaged during the entire spring campaign and summer campaign. And by looking at these contour plots, or these vertical profiles, you can see that there are distinct features which shows the seasonal variability and vertical heterogeneity. Right. So, for example, in terms of seasonal variability, in the springtime, you see a mode size of the aerosols at around 30 nanometer. And then for the summer campaign, you see a mode size of around 100 nanometers. And then you can also see that there are generally lower concentration of aerosols in the upper boundary layer when we're moving up above this to higher altitude above the ground. Right, and normally the let's say the average boundary layer height during the spring and summer campaign were kind of similar between 1,300 to 1,400 meters. So you can see this gradual decrease of the aerosol concentration, which is likely due to the cloud processing or the scavenging. And further, if you look at the springtime, you can further see these relatively high concentration of the nucleation mode aerosols. And this is showing both in the film size range below 20 nanometers, and also the CPC size range between 3 to 10 nanometers. So since these color plots cannot really show you the actual or the exact values of the aerosol concentrations, so we further showed the aerosol size distributions in different size bins. So the first panel here shows the concentration of aerosols above 3 nanometers, where we regard them as the total aerosol concentration. And you can see in the springtime, there is a higher concentration of aerosols at almost all altitudes. And further, we separated this total aerosol concentration into different size bins, for example, 3 to 10 nanometer, 10 to 20 nanometer, 20 to 100 nanometer, and above 100 nanometer. And then for the 3 to 10 and 10 to 20, they are somewhat in the nucleation mode aerosol size range, and they show a lot of similarities. For example, in the springtime, you see a higher concentration of aerosols in the boundary layer, right? And then in the Aitken mode, in the boundary layer, the summer campaign and spring campaign have relatively similar total aerosol concentration or Aitken mode aerosol concentrations. And during the summer campaign, there's a higher concentration of the accumulation mode aerosols in the boundary layer. But you see that overall, the springtime has a higher concentration. So you can see this higher concentration of aerosols is mainly contributed by the nucleation mode that were measured in these or that were shown in these two panels. And also you could see some interesting feature that the mean value of the concentration in these size bins are actually above the 75 percentile, which shows this upper edge of the boxes, which means that there were several new particle formation events, or we call them sporadic strong new particle formation events, that give you really high concentration of aerosols that drives this high concentration of the mean aerosol, and drives this high value of the mean aerosol concentration in the nucleation mode. And further, you can see that in the accumulation mode, the summertime has a higher concentration, which is likely due to the abundance of these condensing vapors. So we can understand that the vertical heterogeneity of aerosols are actually caused by these serious processes or dynamics. For example, the aerosol dynamics, the new particle formation and their location where they're happening, the growth of the aerosols, also the cloud processing, and transport processes can also vary the vertical heterogeneity or vertical distribution of the aerosols. And they can include the mixing in the boundary layer, the long-range transport, entrainment, and convective downward transport. So here, due to the time limit, I will just show two example cases that are showing these interesting features in new particle formation and the convective downward transport. So first about new particle formation. So out of these 38 research flights that were conducted during the high-scale campaign, we saw that there were eight of them observing new particle formation near the surface. So new particle formation at the surface is a common feature, especially in the SGP. But at the same time, we saw around 7 of the new particle formation events occurred in the upper boundary layer. And here, actually, it shows you one of these upper boundary layer new particle formation events. We're quite interested in these type of events because the ground may not be able to capture these new particle formation events, and then these newly formed particles may further grow and contribute to the CCA in the boundary layer. For example, in this event, you see a strong new particle formation event in the altitude between 500 and 1,000 meters. So there's higher concentration of aerosols between 3 to 10 nanometers. And at the same time, this new particle formation event corresponds to a minor dip in the total surface area concentration, which is likely caused by the cloud scavenging and the drizzling effect that remove these larger particles. And also, after these particles are formed, they grow to larger sizes, and further, they can get transported down to the surface. And for example, here you see that when they are growing to larger sizes, the ground will not necessarily observe these nucleation mode aerosols. And this is indeed the case for the ground measurement. You can see that only at the end of the flight measurement, we're starting to see some of these smaller atypical mode aerosols, which are caused by these this upper boundary layer new particle formation event. So we also plotted the flight track for this campaign, where the color represents the ratio between the particles above 3 nanometer over the concentration of particles above 10 nanometer. So you can see that the spatial scale for this upper boundary new particle formation event is also quite big. So I think the upper boundary layer new particle formation mechanism is still a very interesting phenomena and is still under investigation. We'd like to do more studies to try to understand the detailed mechanisms that's associated with the events. So another interesting phenomena that we observed from the high-scale campaign is these convective downward transports. So this phenomenon was first observed during the Go Amazon campaign, where Jian Wang has a very nice study summarizing the features of these events. So basically, during these deep convection events where you have these strong precipitation, then the larger particles or the pre-existing aerosols will get washed out. But at the same time, you're going to see these atypical mode or smaller particles showing up in the boundary layer. And from the Go Amazon campaign, there's strong evidence showing that these particles are transported from the free troposphere, where new particle formation occurs regularly, where you have smaller particles. And at the same time, during these deep convective events, there is also a strong or quick decrease of the equivalent potential temperature, which is an indicator for these downward motions. So we also saw these similar events during the high-scale campaign. So for example, this is one event at the ground where you see the precipitation brought these ultrafine particles to the surface, while the existing accumulation mode aerosols are being washed out. So we saw these during the high-scale campaign, at least from the ground data, we saw 8 similar events out of these 51 days of the ground or the corresponding to the flight campaign days. And for the following year, in 2017, we further identified 37 similar events. So these are, I would say, quite common events. And we could also rule out the possibility of new particle formation during this time period, because these events, many of them occur during the night, and then you don't have the solar radiation, and then the precursor, for example, sulfur dioxide, is also not showing these relatively high concentrations during these periods. So further, during the high-scale campaign, I actually found out a flight measurement that was just around 10 hours after one example event or deep convection event. So similarly, we observed the appearance of these smaller particles during the deep convection event, and there was a strong decrease of the equivalent potential temperature. And then for the flight measurements, we saw a relatively continuous size distribution from the free troposphere to the boundary layer. So we think that this may indicate that these vertical transport of aerosols are happening during the deep convection events at the SGP. And we also calculate the flux of the aerosols during these events, and we found that a single event can bring down the aerosols that are in similar magnitudes compared to the entrainment during a whole day. So in summary, we found that the aerosols at the cloud level over the SGP may not be strongly related to aerosols monitored at the surface. And overall, the vertical heterogeneity of aerosols over the SGP is influenced by aerosol dynamics and transport processes. We give a few examples showing the new particle formation and the convective downward transport. We also have a manuscript that's currently under review, and I would like to acknowledge our funding agencies. So thank you for your attention, and feel free to ask me any questions.